Part 1. Introduction to Gas Giants. What makes Jupiter and Saturn unique? Let's take a moment to look up at the night sky. Among the countless points of light scattered across the darkness, two objects stand out, not because they shine like stars, but because they are something entirely different. Jupiter and Saturn, the giants. These worlds aren't just larger than Earth, they are different in almost every way. They are the gas giants of our solar system, and in this first part of our journey, we'll uncover what makes them so massive, so mysterious, and so incredibly important to everything we know about planets. The term gas giant might sound like science fiction, but it's a very real scientific category. It refers to planets that are composed primarily of hydrogen and helium, the same elements that make up most of the Sun. These worlds lack a solid surface. You can't stand on Jupiter or Saturn. If you tried to land, you'd fall into thick, swirling clouds, crushed by unimaginable pressure, long before reaching anything even remotely solid. There are 4 giant planets in our solar system: Jupiter, Saturn, Uranus, and Neptune, but only Jupiter and Saturn are true gas giants. Uranus and Neptune, which lie even farther out, are often classified as ice giants due to their higher concentrations of water, ammonia, and methane. Let's focus on size for a moment, because when it comes to gas giants, the numbers are absolutely staggering. Jupiter is the largest planet in the solar system. More than 1,300 Earths could fit inside its enormous volume. It's so massive that it contains 2.5 times the mass of all the other planets combined. Saturn, while somewhat smaller, is still a giant by every standard. You could fit about 760 Earths inside it. But here's a fun fact. Despite its size, Saturn is also the least dense planet in the solar system. If you could find a bathtub big enough, Saturn would float in it. Both planets rotate with incredible speed. A day on Jupiter lasts just under 10 hours. Saturn takes a little over 10.5. That means these massive worlds complete a full spin in less than half the time it takes Earth to do the same. This rapid rotation causes their shapes to bulge at the equator, and it drives the fast-moving jet streams and storm systems that make their atmospheres so dynamic and visually stunning. But how did these giants come to be? To answer that, we have to go back in time, about 4.6 billion years, to the early days of the solar system. Imagine a vast cloud of gas and dust slowly collapsing under its own gravity. At the center, the sun ignited, while the remaining material flattened into a spinning disk. Closer to the sun, temperatures were high, and only metals and rocks could solidify. This is where the rocky planets, Mercury, Venus, Earth, and Mars formed. But farther out, beyond what we call the frost line, temperatures dropped low enough for ice to form. This allowed for the rapid accumulation of icy and rocky cores, which then attracted enormous amounts of hydrogen and helium from the surrounding nebula. That's how gas giants like Jupiter and Saturn were born. Jupiter likely formed first, and may have played a role in shaping the entire solar system. Its immense gravity could have flung other growing planetary bodies inward or outward, influencing where planets eventually settled. Saturn formed shortly after, and together, these two giants may have even migrated from their original positions in the early days of planetary development. If we could look inside these planets, we'd find layers upon layers of gas, becoming hotter and denser the deeper we go. At great depths, hydrogen exists in a rare form called metallic hydrogen, a state in which hydrogen behaves more like a metal and can conduct electricity. It's this exotic material that helps generate Jupiter's and Saturn's powerful magnetic fields. At the very core, both planets likely have dense centers made of rock and metal, though no probe has ever reached them. Jupiter and Saturn share many traits, but they also have distinct personalities. Jupiter is bold and dramatic. Its thick atmosphere is striped with colorful bands of clouds, home to violent storms and winds that reach hundreds of kilometers per hour. Most famously, it boasts the Great Red Spot, a colossal storm larger than Earth that has been raging for centuries. It also has the strongest magnetic field of any planet and a terrifying radiation environment that can fry electronics. Saturn, on the other hand, is subtler in color but no less fascinating. Its pale golden hues are wrapped in high-altitude haze. It also experiences massive storms, including one enormous enough to encircle the entire planet. But Saturn is best known for its spectacular rings. These shimmering icy bands stretch hundreds of thousands of kilometers into space and make Saturn one of the most iconic and visually stunning objects in our solar system. Why do gas giants matter so much to us here on Earth? For one, they've played a protective role. Jupiter's gravity is so strong that it can deflect or capture comets and asteroids that might otherwise threaten the inner planets. In that way, Jupiter might be acting like a giant cosmic shield. But the gas giants are also essential to understanding how planetary systems form and evolve. Many of the exoplanets we've discovered around other stars are gas giants, some of them even larger than Jupiter, orbiting perilously close to their suns. By studying our own giants, we gain insight into these alien worlds. Jupiter and Saturn also have fascinating families of moons, some of which are among the most promising places to search for life beyond Earth. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both appear to harbor liquid oceans beneath their icy crusts. Titan, Saturn's largest moon, has lakes of methane and a thick atmosphere. These moons offer tantalizing hints that life in some form might not be limited to our pale blue dot. As we continue our journey through this lecture series, we'll explore each of these giants in greater detail. We'll dive into the atmosphere of Jupiter and explore the secrets swirling beneath its cloud tops. We'll venture into the ringed beauty of Saturn and learn how its rings formed and how they might one day disappear. We'll visit their moons, some volcanic, others frozen, and some perhaps harboring the right ingredients for life. And we'll take a look at the missions that have brought us these insights. Spacecraft like Galileo, Cassini, Juno, and the ones still to come. Jupiter and Saturn are not just planets. They are ancient relics of the solar system's early days. They are laboratories of extreme physics. They are guardians of Earth and windows into other worlds. They challenge us, they humble us, and they inspire us to keep asking big questions. So as we begin this odyssey through the realm of the giants, remember, what lies out there in the cold reaches of the solar system is not just distant. It's deeply connected to everything we are, everything we know, and everything we hope to discover. The gas giants are calling, and this is just the beginning. Part 2. Jupiter, King of the Planets. Jupiter, the name alone evokes power and authority. In mythology, Jupiter was the king of the gods, and the planet that bears his name certainly lives up to the title. It dominates the solar system, not only with its immense size and mass, but with its magnetic might, its dynamic atmosphere, and its influence on everything that orbits the Sun. In this lecture, we step closer to this massive world to understand its structure, its storms, its moons, and the role it plays in shaping the architecture of our cosmic neighborhood. At first glance, Jupiter appears as a golden-white disk in the sky, easily visible to the naked eye, but behind that seemingly calm glow is a planet of extremes. Let's begin with its sheer size. Jupiter is so massive that more than 1,300 Earths could fit inside it. It holds over 70% of all the planetary mass in the solar system. Its gravitational pull is second only to the Sun. That kind of power doesn't just keep a tight grip on dozens of moons. It also affects the orbits of asteroids, comets, and even other planets. Jupiter's rotation is blisteringly fast. It spins once every 9 hours and 56 minutes, making it the fastest spinning planet in the solar system. This rapid spin causes the planet to bulge at the equator, giving it an oblate shape, noticeably wider in the middle than at the poles. It also drives the strong jet streams that shape the planet's distinctive bands and storms. Jupiter's atmosphere is a chaotic masterpiece. It's made primarily of hydrogen and helium, but trace amounts of ammonia, methane, water vapor, and other chemicals give rise to the planet's stunning visuals. The planet is wrapped in colorful cloud bands that encircle it in alternating light and dark stripes. These bands, known as zones and belts, are driven by winds that can reach speeds of over 600 kilometers per hour. And where these bands meet, storms brew. None of those storms is more iconic or more mysterious than the Great Red Spot. This swirling, oval-shaped tempest has been raging for at least 350 years, and probably much longer. At its widest, it was once 3 times the diameter of Earth. Today, it has shrunk to about 1.3 Earths wide, but it's still going strong. Scientists still don't fully understand why it's red, or how it has lasted so long, but it remains one of the most recognizable features in the entire solar system. Beneath Jupiter's cloud tops, the pressure and temperature rise dramatically. As we descend, the hydrogen gas begins to behave more like a liquid. Eventually, under crushing pressure, it turns into metallic hydrogen, a rare and exotic phase that's believed to generate Jupiter's powerful magnetic field. This magnetic field is the largest of any planet, stretching millions of kilometers into space and forming a vast magnetosphere that dwarfs even the Sun. That magnetosphere traps radiation in huge belts, creating an extremely hostile environment for spacecraft. In fact, the Galileo probe, which orbited Jupiter in the 1990s, had many of its instruments damaged or disrupted by this radiation. Juno, the more recent mission launched in 2011, was designed to fly in polar orbits to minimize its exposure. Even so, each close pass by Jupiter's cloud tops is like threading a needle between zones of invisible, deadly energy. And then there are the moons, Jupiter's vast retinue of companions. As of now, scientists have confirmed over 90 moons orbiting Jupiter. 4 of them, known as the Galilean moons, are among the most fascinating objects in the solar system. Discovered in 1610 by Galileo Galilei, these moons, Io, Europa, Ganymede, and Callisto, are miniature worlds in their own right. Io is the most volcanically active body in the solar system. Its surface is constantly reshaped by powerful eruptions, some of which hurl molten sulfur hundreds of kilometers into space. The heat that drives this activity comes from tidal forces, gravitational squeezing caused by Jupiter's immense gravity, and the orbital interactions with the other moons. Europa, in contrast, is a frozen mystery. Its icy surface is crisscrossed by reddish cracks, but beneath it lies a global ocean, possibly twice the volume of all Earth's oceans combined. This subsurface sea is kept warm by internal heat, and where there's liquid water, scientists suspect there might be the ingredients for life. Missions like the upcoming Europa Clipper are set to explore this possibility further. Ganymede is the largest moon in the solar system, even bigger than Mercury. It has its own magnetic field, an icy surface, and strong evidence of an internal ocean. Callisto, the outermost of the four, is an ancient and heavily cratered world, offering a glimpse into the early solar system. Jupiter's moons aren't just interesting on their own. They're also important in understanding how planetary systems form. Some of the smaller, irregular moons may be captured asteroids, while others formed in a disk of gas and dust around Jupiter during its early years. Together, they form a kind of mini-solar system orbiting a gas giant that resembles a failed star. Jupiter's gravity doesn't stop at moons. It also commands entire groups of asteroids. The Trojan asteroids, which share Jupiter's orbit around the Sun, are gathered into two large swarms, one ahead of the planet and one behind. These objects may hold clues about the early solar system and are currently the target of NASA's Lucy mission. Despite its distance, Jupiter has played a crucial role in Earth's history. It may have helped shape the trajectory of water-bearing comets and deflected dangerous objects that might have struck our planet. At the same time, some theories suggest that Jupiter may have disrupted the formation of a super-Earth closer to the Sun. Its gravitational influence has been a double-edged sword, protecting and shaping, but also altering the fates of other would-be planets. Jupiter has also been a favorite target for space missions. The Pioneer and Voyager flybys in the 1970s gave us our first close-up images. The Galileo orbiter studied the planet and its moons for over 7 years. More recently, NASA's Juno mission has provided stunning data on Jupiter's interior, magnetosphere, and polar auroras. Auroras that are the most powerful in the solar system. As we learn more about Jupiter, we begin to see how much it still holds in secret. How deep do its winds really go? What lies at its core? How does metallic hydrogen behave under such intense pressure? And could its moons harbor life in environments completely alien to Earth? Jupiter is more than just a planet. It's a force of nature, a relic from the earliest moments of the solar system. A gravitational juggernaut that continues to shape the cosmos around it. Its beauty is not just in its colorful clouds or its ancient storm. It's in the way it draws us in, scientifically, imaginatively, and emotionally. As we close this chapter and prepare to journey onward to Saturn, remember this: Jupiter may be distant, but it is no stranger. Its influence reaches even to our doorstep. Its mysteries push the boundaries of our knowledge. And its presence, massive and magnificent, reminds us of how vast and wondrous our solar system truly is. Part 3. Saturn, the ringed giant. If Jupiter is the king of the planets, then Saturn is surely its crowned companion. With its stunning rings and golden hue, Saturn is often considered the most beautiful planet in the solar system. But this ringed giant is more than just a visual marvel. Beneath those graceful rings lies a planet filled with storms, mysteries, and contradictions. It is at once elegant and violent, serene and turbulent. In this part of our journey, we'll dive into the world of Saturn, exploring its structure, atmosphere, and magnetic field, and, of course, its mesmerizing rings. Saturn is the second largest planet in the solar system, just behind Jupiter. It's almost 95 times more massive than Earth and nearly 10 times wider. But for all that size, it's remarkably light. Saturn is the least dense planet in the solar system. So light, in fact, that it would float in water. It's a giant ball of hydrogen and helium, with a possible core of heavier elements buried deep within. Like Jupiter, Saturn doesn't have a solid surface. What we see when we look at it are thick bands of clouds, moving at tremendous speeds. Saturn rotates quickly, completing a full spin in about 10.5 hours. This rapid rotation flattens the planet at its poles and causes it to bulge at the equator. The winds in Saturn's upper atmosphere are even faster than those on Jupiter, reaching up to 1,800 kilometers per hour. These high-speed jet streams help create the planet's distinct cloud bands, although they're more subdued in color than Jupiter's. Instead of rich reds and browns, Saturn's clouds are pale yellows, golds, and grays, more like a watercolor painting than Jupiter's oil-based drama. But Saturn's atmosphere isn't calm. Every few decades, a massive storm erupts in its northern hemisphere, large enough to wrap around the entire planet. These global-scale tempests are known as great white spots. They are seasonal and likely linked to Saturn's long orbit around the Sun, which takes about 29.5 Earth years. When one of these storms breaks out, it lights up the planet in visible and radio wavelengths, giving scientists a front-row seat to the violent weather that brews beneath Saturn's calm appearance. One of Saturn's most iconic and baffling features lies at its north pole, a hexagon. Yes, a six-sided storm system larger than Earth sits at the top of the planet. This strange and persistent pattern was first observed by the Voyager spacecraft in the 1980s, and later studied in detail by the Cassini mission. The hexagon is not just a surface feature, it's a deep and complex atmospheric phenomenon. Scientists believe it's caused by a standing wave in the jet stream, similar to patterns seen in rotating fluids on Earth, but nothing else in the solar system compares to it in scale or stability. Deep inside Saturn, the pressure becomes so intense that hydrogen is squeezed into its metallic form, just like in Jupiter. This layer likely generates Saturn's magnetic field, although its field is weaker and more symmetrical than Jupiter's. Even so, Saturn's magnetosphere extends far into space, capturing charged particles from the solar wind and forming radiation belts that swirl around the planet. Of course, we cannot speak of Saturn without talking about its rings. They are what make Saturn instantly recognizable and unforgettable. While other gas giants also have ring systems, none are as large, bright, or complex as Saturn's. The rings stretch over 280,000 kilometers from the planet, but they're incredibly thin, only about 10 meters thick in most places. They're made almost entirely of ice particles, ranging from tiny grains to massive chunks the size of buildings. These icy particles orbit Saturn in an intricate, layered ballet, shaped by gravity, collisions, and the influence of nearby moons. The rings are divided into main sections labeled A through G, with the A, B, and C rings being the most prominent. Between the A and B rings lies the famous Cassini division, a dark gap caused by gravitational interactions with the moon, Mimas. There are also spiral density waves, propeller-shaped gaps, and shepherd moons that help keep the ring edges sharp and defined. It's a system of astonishing complexity and beauty. But the rings won't last forever. Observations suggest they are slowly falling into Saturn, pulled down by the planet's gravity in a process sometimes called ring rain. Microscopic particles are constantly being lost, either through collisions or by being drawn into Saturn's upper atmosphere. It's estimated that the rings may be gone in as little as 100 million years, a blink of an eye in cosmic time. This raises an important question. Did Saturn always have rings, or did they form relatively recently? One theory suggests the rings may be the remains of a shattered moon or a passing comet torn apart by Saturn's gravity. Another possibility is that the rings formed during the early days of the solar system but have been reshaped and thinned over time. Whatever their origin, they are temporary, and we are lucky to be living in an age when they can still be admired. Saturn also has a vast collection of moons, at least 146 confirmed so far, with more likely to be discovered. Some are tiny irregular chunks of ice and rock, but others are major worlds in their own right. Titan, Saturn's largest moon, is bigger than Mercury and has a thick atmosphere rich in nitrogen. Enceladus, a smaller but equally fascinating moon, has geysers of water ice that erupt from cracks near its south pole. These icy jets feed one of Saturn's faint outer rings and suggest the presence of a subsurface ocean, one that could potentially harbor life. The exploration of Saturn reached its peak with the Cassini mission, a joint project between NASA, the European Space Agency, and the Italian Space Agency. Launched in 1997, Cassini arrived at Saturn in 2004 and spent 13 years studying the planet, its rings, and its moons. It dropped a probe, Huygens, onto the surface of Titan, giving us the first images of a world with lakes of methane and ethane. It flew through the icy plumes of Enceladus and watched storms develop in Saturn's atmosphere. Cassini's data transformed our understanding of the ringed giant and gave us thousands of breathtaking images. When the mission ended in 2017, Cassini plunged into Saturn's atmosphere to avoid contaminating any of the potentially habitable moons. Saturn is a planet of contrasts. It is delicate and ferocious, familiar and alien. It's the jewel of the solar system, a world that captures the imagination of scientists and dreamers alike. Its rings may be fleeting, but the knowledge they bring is enduring. As we gaze at Saturn through telescopes or sift through data from distant spacecraft, we're not just admiring a beautiful planet. We're uncovering the forces that shape planetary systems, the history written in ice and gas, and the possibilities that lie beyond our own world. Saturn doesn't shout, it sings. Its elegance lies in the quiet persistence of motion, the icy particles dancing in orbit, the clouds drifting in bands, the moons keeping time like clockwork. It reminds us that even in the cold outer reaches of the solar system, wonder is everywhere. As we leave the serene but powerful presence of Saturn, we turn our eyes outward, not to another planet, but to the worlds that orbit these giants, moons with lava and ice, with hidden oceans and alien skies. In our next lecture, we'll explore Jupiter's moons, a system within a system, and perhaps the next great frontier in our search for life. Part 4. The Moons of Jupiter, a mini-solar system. When Galileo Galilei first turned his telescope toward Jupiter in 1610, he made a discovery that changed the world: 4 tiny points of light orbiting the planet. These were not stars. They were moons, worlds in motion around another world. It was the first time anyone had seen clear evidence that not everything in the heavens revolved around Earth. Today, we call them the Galilean moons: Io, Europa, Ganymede, and Callisto. And though Galileo didn't know it then, those 4 moons were just the beginning. As of now, Jupiter is known to have over 90 moons. They range from tiny captured asteroids to vast, complex worlds with volcanoes, ice shells, magnetic fields, and possibly even oceans of liquid water. In this lecture, we explore the moons of Jupiter, an astonishing collection that makes the planet feel like a solar system in miniature. Let's begin with the largest and most famous group, the Galilean moons. Each of these 4 is a world in its own right, larger and more complex than many planets. The innermost of the group is Io, a tortured, fiery world constantly pulled and squeezed by Jupiter's gravity. That squeezing, a result of tidal forces, generates immense internal heat. The result is the most volcanically active body in the entire solar system. Lava erupts from giant calderas, reshaping the surface regularly. Unlike most moons, Io has almost no craters. Its surface is being constantly renewed, Its yellow, orange, and red colors come from sulfur compounds, making it look almost like a diseased marble. But Io is not just a volcanic oddity. It plays a key role in Jupiter's environment. Its eruptions eject material into space, creating a torus of plasma around Jupiter and helping fuel the giant planet's magnetic field. Next comes Europa. At first glance, Europa is quiet and icy, a smooth, pale moon covered in intersecting cracks and ridges. But beneath its frozen crust lies one of the most intriguing features in the solar system: a global subsurface ocean. This ocean may contain more than twice the water of all Earth's oceans combined, and it is kept liquid by heat generated through tidal flexing. The cracks and streaks on Europa's surface are evidence of shifting ice plates and possible upwellings of warmer material from below. Every so often, plumes of water vapor have been detected erupting into space. This suggests that material from the ocean may be making its way to the surface and beyond. For scientists searching for life beyond Earth, Europa is a tantalizing target. A saltwater ocean, a source of heat, and organic materials. All the ingredients we think are necessary for life may be hidden beneath just a few kilometers of ice. The third Galilean moon, Ganymede, holds a special title. It is the largest moon in the solar system. Bigger than Mercury and nearly the size of Mars, Ganymede is the only moon known to generate its own magnetic field. It has a complex surface with bright icy regions and darker, older areas marked by impact craters. Beneath its icy crust, Ganymede likely has a layered interior, including a liquid water ocean and possibly a metallic core. The presence of a magnetic field and an internal ocean makes Ganymede another prime candidate in the search for extraterrestrial habitability. In recent years, observations have confirmed that the moon has a very thin atmosphere and auroras that dance near its poles. These auroras interact with Jupiter's magnetic field, providing clues about Ganymede's internal structure. Finally, we come to Callisto, the most distant of the four Galilean moons and perhaps the most ancient. Callisto's heavily cratered surface tells a story of great age and stability. Unlike its siblings, Callisto has little geologic activity. It has no large-scale tectonics, no volcanoes, and no signs of resurfacing. Yet, this quiet moon may still harbor a subsurface ocean. Its surface is studded with impact basins, the largest of which, Valhalla, spans thousands of kilometers and shows a remarkable ringed pattern. Callisto represents a different kind of possibility. While it may not be a dynamic place like Europa or Io, its lack of internal activity could make it one of the safest locations in the Jovian system for future human exploration. Some mission planners even consider Callisto a potential base camp for missions deeper into the outer solar system. Beyond the Galilean moons lies an array of smaller and more irregular satellites. Many of these are believed to be captured asteroids or leftover fragments from early collisions. Some of the more notable ones include Amalthea, a reddish irregular moon that orbits very close to Jupiter, and Thebe, which helps feed the planet's faint inner ring. These small moons may seem insignificant compared to the giants, but they play important roles in shaping Jupiter's ring system and contributing material to the planet's magnetosphere. Speaking of rings, it might come as a surprise that Jupiter has them too. Discovered by the Voyager spacecraft, Jupiter's rings are thin, dark, and faint, made mostly of dust ejected by impacts on the inner moons. They are not nearly as dramatic as Saturn's, but they offer further evidence of the complex interplay between Jupiter and its moons. The relationships among Jupiter's moons are not just gravitational, they are dynamic, mathematical, and precise. Io, Europa, and Ganymede are locked in what's called a Laplace resonance. For every one orbit of Ganymede, Europa orbits twice, and Io orbits 4 times. This resonance maintains tidal heating within the moons and keeps their interiors active. It's a delicate and beautiful orbital dance, one that continues to shape these worlds over billions of years. Jupiter's moons have also been targets of scientific exploration for decades. The Galileo spacecraft, launched in 1989, orbited Jupiter from 1995 to 2003 and conducted flybys of the Galilean moons. It confirmed the volcanic activity on Io and gathered strong evidence for subsurface oceans on Europa and Ganymede. More recently, the Juno mission, while primarily focused on Jupiter itself, has provided valuable data on the planet's magnetosphere and the influence of its moons. Looking ahead, 2 major missions are set to explore these moons further. NASA's Europa Clipper will launch in the late 2020s to study Europa's ocean, geology, and habitability. Meanwhile, the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, will focus on Ganymede, Callisto, and Europa, aiming to characterize their oceans and assess their potential to support life. The idea that a planet's moons might harbor alien life is no longer science fiction. It is a scientific goal, one we are rapidly approaching with robotic explorers and advanced instruments. The moons of Jupiter are not passive, frozen rocks. They are active, evolving, and, some of them, potentially habitable. What makes this system so extraordinary is its diversity. In just one corner of the solar system, we find the most volcanic object, some of the oldest untouched terrain, the largest moon, and maybe even a liquid ocean with alien life swimming beneath the ice. It is a reminder that when we explore the solar system, we are not simply hopping from planet to planet. We are uncovering entire ecosystems of celestial bodies, each with their own story to tell. As we leave the realm of Jupiter's moons, we shift our attention to another fascinating world. Saturn, too, has a rich and diverse collection of moons, some icy and mysterious, others huge and hazy, and one in particular that has rivers and lakes unlike anything else we've seen. In our next lecture, we'll travel to Titan, Enceladus, and the other satellites of Saturn, the hidden treasures of the ringed giant. Part 5. The Moons of Saturn, Enceladus, Titan, and beyond. Saturn is not alone in its orbit around the Sun. Like Jupiter, it is surrounded by a vast entourage of moons, more than 140 at last count, with more likely waiting to be discovered. But these are not just icy rocks drifting in the void. Some of Saturn's moons are among the most intriguing and scientifically important bodies in the entire solar system. They include worlds with underground oceans, towering geysers, dense atmospheres, and chemical ingredients that might support life. In this lecture, we explore the moons of Saturn, focusing on the enigmatic Enceladus, the massive and mysterious Titan, and the other icy satellites that make this system a treasure trove of planetary science. Let us begin with Titan. It is the largest of Saturn's moons, and the second largest moon in the solar system, only slightly smaller than Jupiter's Ganymede. In fact, Titan is larger than the planet Mercury. But what makes Titan truly unique is its atmosphere. Unlike any other moon, Titan has a thick, hazy shroud that completely hides its surface from view in visible light. This atmosphere is primarily composed of nitrogen, with small amounts of methane and other organic compounds. It's denser than Earth's, and it supports weather systems, clouds, wind, and even rain. Titan is the only known world other than Earth where we've observed stable bodies of liquid on the surface. But instead of water, Titan's lakes and rivers are filled with methane and ethane, hydrocarbons that are gases on Earth but behave like water in Titan's frigid climate. The surface temperature hovers around -179 degrees Celsius. Despite the cold, the landscape looks eerily familiar. Dunes of organic particles stretch across vast plains. River channels wind through hills. Lakes glitter near the poles. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, used radar to peer through Titan's atmosphere and revealed a world that feels strangely Earth-like, yet profoundly alien. In 2005, Cassini deployed a probe called Huygens, which descended through Titan's atmosphere and landed on its surface. It was the first and only landing on a moon in the outer solar system. For about 90 minutes, Huygens transmitted data and images back to Earth. It showed a landscape of rounded ice pebbles and a distant ridge, possibly the shore of an ancient methane stream. The success of the Huygens mission opened up new questions. Could there be life in Titan's lakes, based not on water but on methane chemistry? Is there a subsurface ocean of liquid water beneath the icy crust? These questions remain open, and NASA is preparing to return to Titan with a new mission called Dragonfly, a drone-like rotorcraft that will explore the moon from the air starting in the mid-2030s. If Titan is Saturn's most famous moon, Enceladus may be its most surprising. It's a small moon, only about 500 kilometers in diameter, but what it lacks in size, it makes up for in activity. When Cassini flew by Enceladus, it discovered geysers of water ice shooting out from the South Pole. These jets originate from long fissures in the surface called tiger stripes, and they contain not only water vapor, but also salts, methane, carbon dioxide, and organic molecules. Cassini even flew through the plumes, sampling their contents directly. The presence of these geysers implies an internal ocean of liquid water beneath Enceladus's icy shell. Heat generated by tidal forces, caused by Saturn's gravitational pull, keeps part of the ocean warm and allows it to escape through the surface. The material from these geysers forms one of Saturn's faint outer rings, the E-ring. But what excites scientists the most is the possibility that Enceladus's ocean, like Europa's at Jupiter, could support microbial life. It has water, energy, and complex chemistry, key ingredients for life as we know it. Enceladus is now one of the top targets in the search for extraterrestrial biology. Future missions could return to sample its plumes in greater detail, or even deploy landers near the tiger stripes. For now, though, Enceladus remains one of the most tantalizing mysteries in the outer solar system. A tiny moon that might hold secrets of life beneath its frozen skin. Saturn's moons don't stop there. Consider Mimas, a small, heavily cratered moon that looks remarkably like the Death Star from Star Wars. Its most prominent feature is a massive impact crater called Herschel, which spans almost a third of the moon's diameter. For a long time, Mimas was thought to be geologically dead, but recent studies have suggested the possibility of a subsurface ocean, though that remains controversial. Then there's Tethys, another icy moon, with a massive canyon system called Ithaca Chasma. Theories suggest that this great scar may have formed as the moon's internal ocean froze, expanding and cracking the surface. Dione and Rhea, two other mid-sized moons, also show signs of past geological activity, with fractured surfaces and possible internal oceans. All of these moons are primarily made of water ice, which behaves like rock in their cold environments. Hyperion, one of the more bizarre moons, is shaped like a sponge and tumbles chaotically through space. It has an incredibly low density and is filled with deep craters that make it look like a pumice stone. Phoebe, an irregular outer moon, orbits in the opposite direction to most of Saturn's moons, suggesting it may be a captured object from the Kuiper belt, a leftover from the early solar system. Saturn's moons also play a key role in shaping and maintaining its rings. Some, like Pan and Daphnis, orbit within the rings and act as shepherds, keeping ring particles in line and creating gaps. Others, like Janus and Epimetheus, share nearly the same orbit and perform a celestial dance, swapping positions every few years. The interactions between moons and rings are complex and dynamic, creating ripples, waves, and intricate structures that continue to fascinate scientists. The Cassini mission was instrumental in uncovering the secrets of Saturn's moons. Over its 13 years in orbit, Cassini performed dozens of flybys, capturing high-resolution images, sampling atmospheres and plumes, and mapping surfaces in unprecedented detail. It transformed our understanding of these distant worlds. But perhaps its greatest legacy was shifting the focus of astrobiology beyond planets and toward moons. Before Cassini, few would have guessed that tiny Enceladus could be a place to search for life. Now, it's at the top of the list. What's most striking about Saturn's moons is their diversity. Within a single planetary system, we find a smoggy world with lakes of methane, an ice-covered ocean moon with erupting geysers, cratered relics of the early solar system, and tiny shepherds guiding a magnificent ring system. These moons show us that even the smallest bodies in space can be dynamic, active, and full of surprises. They also challenge our ideas about habitability. Life, we once assumed, required a planet like Earth, moderate temperatures, a stable atmosphere, and liquid water on the surface. But Saturn's moons, like those of Jupiter, suggest that life might be possible in places that are cold, dark, and hidden beneath miles of ice. The ingredients for life may be more common and more varied than we ever imagined. As we leave the icy moons of Saturn behind, we turn next to one of the most beautiful features in all of astronomy: Saturn's rings, and the lesser-known but still fascinating rings of Jupiter. These vast, delicate structures are not just ornaments. They are dynamic systems shaped by gravity, collisions, and time. In our next lecture, we'll explore the rings of the gas giants, what they're made of, how they formed, and what they're slowly becoming. Part 6. The Rings of Saturn and Jupiter, Beauty and Science. When we think of Saturn, we think of rings. Elegant, shimmering, and vast beyond belief. They are the most iconic feature of any planet in the solar system. But Saturn isn't the only planet with rings. Jupiter has them too, though they're far more subtle. In this lecture, we explore the rings of these two gas giants, not just as celestial ornaments, but as dynamic, evolving systems full of scientific secrets. From icy boulders to dusty halos, the rings of Jupiter and Saturn are windows into the past, revealing the forces that continue to shape our solar system today. Let us begin, of course, with Saturn. Its rings are breathtaking, so large they could stretch from Earth to the Moon and still be visible from space. They are made mostly of water ice, with particles ranging in size from microscopic grains to chunks as large as small houses. When viewed through a telescope, these rings seem solid, like discs of smooth glass. But in reality, they are enormous fields of countless icy particles, orbiting Saturn at high speeds, each following its own path within a narrow range of altitude. The rings are astonishingly thin. Though they stretch more than 280,000 kilometers across, they are typically only about 10 meters thick, thinner, proportionally, than a sheet of paper stretched across a football field. Yet within this delicate structure lies incredible complexity. The main rings are labeled alphabetically in the order they were discovered: A, B, C, D, E, F, and G. The A and B rings are the brightest and most massive. Between them lies the Cassini division, a dark gap caused by gravitational interactions with one of Saturn's moons, Mimas. The C ring is fainter, closer to the planet, and more diffuse. Some of Saturn's outer rings are maintained by so-called shepherd moons, tiny satellites like Prometheus and Pandora that orbit near the edges of rings and help keep them narrow and well-defined. These moons exert just enough gravity to herd the particles, sculpting them into sharp boundaries or creating waves and gaps. The narrow, braided F ring is particularly dynamic, with structures that change in real time due to the constant tug-of-war between shepherd moons. The particles in Saturn's rings are not just orbiting idly. They collide, bounce, stick, and shatter. These interactions generate heat, change orbits, and even form temporary clumps that can last for years. The rings are like a giant laboratory for studying the physics of disks, similar in structure to the disks that form around young stars where planets are born. Understanding how rings behave helps us understand how solar systems form. But how did Saturn's rings themselves form? That question remains a topic of debate. One theory suggests that the rings are remnants of a shattered moon, perhaps a large icy body that wandered too close to Saturn and was torn apart by tidal forces. Another idea is that they date back to the early days of the solar system, leftovers from the disk of material that formed Saturn itself. Data from the Cassini spacecraft suggests the rings may be relatively young, perhaps only 100 million years old, based on how clean and bright they appear. If true, we are lucky to be living in the brief moment in cosmic time when the rings are visible. Even more fascinating is the fact that the rings are disappearing. Slowly but surely, particles from the rings are being pulled into Saturn's atmosphere by gravity and electromagnetic forces. This phenomenon, known as ring rain, means the rings are shrinking. Over millions of years they may fade away entirely. What we see now, those glorious arcs of light, is only temporary. A fleeting masterpiece of cosmic architecture. While Saturn's rings take center stage, Jupiter also wears a faint, almost ghostly halo. Jupiter's ring system was discovered in 1979 by the Voyager 1 spacecraft. It consists of three main components: the halo ring, the main ring, and the gossamer rings. These rings are made mostly of tiny dust particles, far smaller than the icy blocks in Saturn's rings. They are almost invisible in visible light and were only revealed through careful imaging and by observing how light was scattered through them. Jupiter's main ring is relatively thin and flat. It lies just outside the planet's equator and is formed primarily from dust ejected by impacts on two small inner moons, Amalthea and Thebe. When micrometeoroids strike these moons, they kick up dust which then orbits Jupiter and gradually forms a diffuse ring. The gossamer rings extend beyond the main ring and are even fainter, composed of similar dust from the same moons. One of the most interesting aspects of Jupiter's rings is their dynamic behavior. Because the particles are so small, they are strongly influenced by Jupiter's powerful magnetic field. Charged particles spiral around magnetic field lines, creating a complex structure that interacts with the planet's radiation belts. Unlike Saturn's icy ring particles, which are relatively stable, the particles in Jupiter's rings are constantly replenished, scattered, and destroyed. Why are Saturn's rings so prominent, while Jupiter's are so faint? Much of it comes down to mass and material. Saturn's rings have a huge volume of water ice, reflecting sunlight beautifully. Jupiter's rings, by contrast, are made of dark dust that doesn't reflect much light. Saturn's environment also seems to favor the preservation of large icy bodies, while Jupiter's intense radiation and gravity likely prevent the formation of stable icy rings. Another key difference lies in their interactions with moons. In Saturn's system, the rings and moons are closely intertwined. Moons shape the rings, clear gaps, and even form mini-moons within the rings themselves. In Jupiter's case, the moons mostly feed the rings with dust from impacts. These two systems offer complementary perspectives. Saturn shows us a grand, icy structure governed by elegant gravitational dance. Jupiter shows us a more chaotic, ever-changing system built from dust and shaped by radiation. The study of planetary rings doesn't just tell us about the gas giants. They also help us understand the history of our solar system. Rings can capture debris from ancient collisions, act as time capsules of past events, and reveal how gravity and motion work on large scales. And beyond our solar system, rings have even been proposed as possible features around exoplanets. Though we haven't seen them directly, some strange dimming patterns in distant star systems could hint at ringed worlds orbiting other suns. The Cassini mission was especially vital in advancing our understanding of rings. Over 13 years, it studied Saturn's rings in exquisite detail, mapping their structure, measuring their composition, and observing how they change over time. Cassini even made daring dives between Saturn and its innermost rings during its final mission phase, gathering data no other spacecraft had ever obtained. It revealed that the rings are more dynamic, more massive, and more complex than anyone had imagined. As we look toward the future, the rings of the gas giants remain a compelling area of research. How do these systems evolve? Could new rings form if another moon were destroyed? Could moons grow out of the rings, as some models suggest happened in the past? And how do these seemingly fragile structures survive in the harsh environments around giant planets? The rings of Saturn and Jupiter remind us that beauty in space often comes from movement, from particles colliding, moons nudging, forces tugging. They are not static decorations, but living systems. And in their graceful arcs and ghostly glows, they carry stories billions of years old. As we prepare to conclude our exploration of the gas giants, we turn next to the spacecraft and missions that have made these discoveries possible. In our final lecture, we'll look at the past, present, and future of space exploration around Jupiter and Saturn, and the questions that still remain as we seek to understand the giants that rule our solar system. Part 7. Exploration and Future Missions to Jupiter and Saturn. The story of Jupiter and Saturn is one that spans billions of years, but our understanding of these gas giants is very recent. For most of human history, they were just bright wandering stars in the night sky, enigmatic, distant, and unreachable. But in the last few decades, we've crossed that distance. We've sent machines to fly by, to orbit, even to plunge into their atmospheres. These spacecraft have transformed points of light into dynamic worlds, filled with storms, oceans, rings, and possibly even the ingredients for life. In this final lecture, we'll retrace the history of exploration at Jupiter and Saturn, examine the extraordinary missions that unveiled their secrets, and look ahead to the journeys yet to come. The first close encounters with Jupiter and Saturn came in the 1970s through NASA's Pioneer and Voyager programs. Pioneer 10, launched in 1972, was the first spacecraft to fly past Jupiter in 1973, followed a year later by Pioneer 11, which went on to visit Saturn in 1979. These early missions gave us our first up-close look at the gas giants and their environments. We saw Jupiter's swirling clouds and powerful magnetic field. We glimpsed Saturn's dazzling rings from just a few 100,000 kilometers away. These images were blurry by today's standards, but they were historic, replacing centuries of speculation with real data. Then came the Voyagers. Launched in 1977, Voyager 1 and Voyager 2 took advantage of a rare planetary alignment that allowed them to perform gravity-assist flybys, slingshotting from one giant to the next. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, sending back spectacular images of the Great Red Spot and revealing the full grandeur of Saturn's ring system. Voyager 2 followed with flybys of Jupiter, Saturn, Uranus, and Neptune, becoming the only spacecraft to visit all 4 outer planets. The discoveries from the Voyager missions were staggering. They revealed active volcanoes on Io, an ice-covered Europa, Ganymede's groove terrain, and strange cratered Callisto. At Saturn, they found the mysterious hexagon at the North Pole, the structure of the rings, and a hazy moon called Titan with a thick atmosphere. These missions expanded our understanding of planetary science and laid the foundation for future exploration. But flybys could only show so much. To really understand these worlds, we needed to stay a while. That opportunity came with NASA's Galileo mission, launched in 1989. After a 6-year journey, Galileo became the first spacecraft to orbit Jupiter in 1995. Over the next 8 years, it studied the planet and its moons in detail, performing multiple flybys of the Galilean satellites. Galileo confirmed the existence of a liquid ocean beneath Europa's surface, observed volcanic eruptions on Io, and mapped Jupiter's intense radiation belts. Galileo also carried an atmospheric probe, which it released into Jupiter's upper layers in December 1995. As it descended, it measured temperature, pressure, wind speeds, and chemical composition. It revealed unexpected dryness, complex weather systems, and a surprisingly deep layer of atmospheric circulation. The probe was eventually crushed by pressure and heat, but it provided valuable data during its short descent. While Galileo was orbiting Jupiter, attention began to shift to Saturn. In 1997, NASA, in partnership with the European and Italian space agencies, launched the Cassini-Huygens mission. Cassini arrived at Saturn in 2004 and would go on to become one of the most successful planetary missions ever conducted. Over 13 years, Cassini orbited Saturn 294 times and conducted more than 100 flybys of its moons. The discoveries came quickly. Cassini found seasonal changes in Saturn's atmosphere, giant storms that wrapped around the planet, and new details about its magnetic field. It mapped the structure of the rings in stunning detail, revealing propeller-shaped gaps, vertical waves, and mini-moons embedded within the ice. But the most groundbreaking discoveries came from Saturn's moons. The Huygens probe landed on Titan in 2005, becoming the first spacecraft to touch down on a body in the outer solar system. It revealed a world with methane rivers, hydrocarbon lakes, and an atmosphere rich in organic molecules. Cassini also flew through the plumes erupting from Enceladus and detected water vapor, ice grains, salts, and organic compounds, direct evidence of a subsurface ocean and possibly hydrothermal vents on the seafloor. These findings fundamentally changed the way we think about habitability. It was no longer just Earth-like planets that could support life. Icy moons with oceans beneath their surfaces were now on the list. Enceladus and Europa became prime targets for astrobiology. Cassini's mission ended in 2017 with a dramatic plunge into Saturn's atmosphere, a maneuver designed to avoid contaminating any potentially habitable moons. More recently, we've been learning from the Juno spacecraft, which arrived at Jupiter in 2016. Unlike Galileo, Juno orbits the planet in a highly elliptical, polar orbit that avoids the worst of the radiation. Juno's mission is to study Jupiter's interior, gravity field, magnetic field, and polar magnetosphere. It has revealed that Jupiter's atmosphere extends much deeper than previously thought, that the Great Red Spot penetrates far below the clouds, and that the core may be more diffuse and mixed than expected. Juno has also taken unprecedented images of Jupiter's polar auroras, giant glowing rings of energy caused by the planet's magnetic field and charged particles. Juno has been extended several times and now includes flybys of some of Jupiter's moons, including Ganymede and Europa. These close passes have already provided high-resolution images and helped plan for future missions. And those missions are on the way. In the coming decade, 2 major spacecraft will continue the exploration of Jupiter's system. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, launched in 2023 and will arrive in 2031. It will conduct flybys of Europa and Callisto before settling into orbit around Ganymede, making it the first spacecraft to orbit a moon other than our own. JUICE will study Ganymede's magnetic field, internal ocean, and surface composition. Meanwhile, NASA's Europa Clipper is scheduled for launch in 2024, with arrival at Jupiter in the early 2030s. It will perform dozens of close flybys of Europa, searching for signs of habitability. The spacecraft will carry instruments to image the surface, analyze the chemistry of any plumes, and probe the thickness of the ice crust. Europa Clipper represents the most focused effort yet to determine whether an ocean moon could support life. On the Saturnian front, the next major mission is Dragonfly. This ambitious NASA mission will send a flying drone to Titan. Scheduled for launch in 2028 and arrival in the mid-2030s, Dragonfly will hop across Titan's surface, analyzing organic chemistry and seeking out environments that could support, or once have supported, life. It's the first rotorcraft mission beyond Earth, and it will mark a major leap in planetary exploration. As we look even further ahead, scientists are proposing missions to return to Enceladus, perhaps to sample its plumes more directly, or even land on the surface. Others imagine deep probes that could descend into the atmospheres of Jupiter and Saturn to study their inner structure, or orbiters that could stay long-term around moons like Titan or Ganymede. There are even concepts for submarines that could one day explore Titan's methane lakes or Europa's ocean. The exploration of Jupiter and Saturn has taught us many things, but it has also revealed how much we don't know. What is the true nature of their cores? How do their magnetic fields evolve over time? What processes drive weather systems on such enormous scales? Could life exist in alien oceans, powered not by sunlight but by chemical energy? Jupiter and Saturn are no longer just distant points of light. They are complex, living worlds. Worlds we have visited, mapped, and touched through our robotic explorers. They remind us that the solar system is not static, not dead, but dynamic and full of surprises. They challenge us to keep going, to keep asking, to keep exploring. And so, as we conclude our 7-part journey through the gas giants, we find ourselves not at the end, but at a beginning. A new era of exploration is just around the corner. With each mission, each flyby, each landing, we step closer to understanding not just these giants of the solar system, but the forces that shape planets, the environments that nurture life, and our place in the cosmic story. Jupiter and Saturn are still calling, and humanity is still listening.